Chapter 4A, Confidence Intervals and Central Limit Theorem. In this activity, we're going to start thinking about statistical judgment and how we can apply and use statistics to draw conclusions. Make sure you've read through why we're studying this, the learning objectives, and our new vocabulary for Chapter 4. Chapter 4 is a longer chapter, so it's broken up into parts A and B. Part A has a lot of examples, so this is broken up into 2 videos. And this video will cover examples 1 through 4. So you'll see some of the familiar concepts, but some new formulas in here. We're going to be working with population proportions that correspond with categorical data, so you'll notice the formulas look a little different than our standard deviation formula for quantitative data. So example 1 investigates color proportions for M&Ms, and there's a video about watching how Mars makes M&Ms that you can watch. I'll link to this in our Canvas page. So one of the employees at the factory in Hackettstown claims that all M&M factories in the U.S. produce an equal number of each of the 6 colors of M&Ms. So we will investigate this claim in our discussion question. Since it's not practical for us to visit each M&M factory in the U.S., we use sample data and sampling techniques to investigate. So think about, we want to investigate if the proportion of blue M&Ms in a random sample of M&M candies is equal to the proportions of the other colors. So we want to think about what types of results are going to support the factory employee's claim. So we say if there are equal amounts of the 6 colors, this supports the employee claim. If we find an unusually large amount of blue M&Ms or an unusually small amount of blue M&Ms, then there are problems with the employee's claim. Since we're interested in predicting the proportion of blue M&Ms, this is categorical data. So our variable x here that represents the color is a categorical variable. The population for this activity is all US M&Ms because if you look back to how the employee made the claim, the employee's claim is that all M&Ms factories in the US produce these equal numbers of each of the 6 colors. So in most cases, statisticians cannot know the population proportion. For example, if we're surveying people about their political opinions, we can only use survey data. We don't know how everyone in the whole population feels. In this situation, the M&M factory employee is making a claim about the parameter, which is the population proportion for each color. So according to the M&M factory employee, we want to think about what is the population proportion that we'll call P for blue M&M candies. We use P for proportion here. So if all 6 colors are equal, then the proportion that we expect of blue M&Ms is 1 out of 6. So we say the population proportion for the claim is 1 out of 6. Each student starts with a sample of 10 M&Ms. So in this case, in the video, I'm going to talk through how you do it. If we have class time, we'll do it in class. If not, you're welcome to get a pack of M&Ms and randomly count out 10 M&Ms and record the amount of blues in your packet. So each student is going to have a different value if they randomly count out 10 M&Ms and then count the numbers that are blue and then find the proportion. The proportions will range from 0, which would be a student who had no blue, to 1, which would be a student who had all 10 out of 10 M&Ms blue. That would be very unusual, I think, to have 10 out of 10 M&Ms blue. So, is the proportion of blue M&Ms from your individual sample a reasonable estimator for the proportion of blue M&Ms coming from all factories in the U.S.? So since we expect variability in sampling, an individual sample is not a reasonable estimator. We know just by chance one sample might be different. Now, if you think back to the law of large numbers that we discussed last activity, the law of large numbers says if we do very many samples, we expect to see a pattern. So we expect there to be some variability in samples, meaning that the proportions in a sample are going to be different from the parameter, that's the population value. But overall, things should not be surprisingly different. So to get a reasonable sense for the parameter, we use a dot plot to look at the proportion of blue M&Ms. So this is from a class I taught last semester, And students figured out their proportion of blue M&Ms and then put this dot plot up here. So here we see there's definitely a peak at 0.1. That would be 1 out of 10 M&Ms were blue. And that's close to the 1 out of 6, or 0.01667 as a decimal. But we also here have a peak at 0.3 in this class data.